Good weekend? All right, should I ruin it for you?
Yes.
Yes? All right. Any questions so far? Homework's easy? Come on, this is like a... All right, let me just put this thing here and... All right, so let me just respond to something that just came. Okay, so last time we looked at the one-link robot, basically a movement through one hinge, which is very common. And when you think about robots, it's really not about the movement. It's about what you want to reach. So when a robot is actually moving, what is moving that? You know, it's an angular displacement, right? So it's usually a motor. So some of the problems that we did, you know, we call it inverse and then, and then straight. We basically said that we have X and Y, and then we said we wanted to know the L and theta. But the inverse of that was we have the L and theta, and we want to know X and Y. And that's more like a real problem, because when you want to move your robot, you want to make sure, you want to find out where the head of that robot is. So what moves that robot is the motor, which is at the hinge, and you basically control the angular displacement of that robot. Therefore, you want to know where the head, the tip ends up. When you want to pick something up, lift it up to a certain location. So it becomes more like an engineering problem. So that was a very simple, I guess, study of robots. The next one, of course, is a little bit more complicated. So now instead of having one link, now you have two links. Okay? A two-link robot. So what do we have? Before we had one arm going like this. Now we have this. You see this? It's a two-link robot. So in this case, the difference between a one-link and a two-link is the extra motor that we have. In other words, we would have one over here, and we would have one over there. Again, same as before, we are assuming that the robot arms are rigid, therefore they are not going to change in size. What we are changing really is the angular displacement, theta 1 and theta 2. You may say, well, why don't we measure theta 2 with regards to the x-axis? But the fact of the matter is the motor is at the tip of that bar. So the angular displacement is relative to this. So if you instruct the motor 1 to move by, say, I don't know, pi over 4 radian, then you instruct the second one to move by pi over 3 radian. But the way it is that that motor is going to be relative to where it is, which is at the head of that arm. Okay? So what is the objective? The objective is, if we know L1 and theta 1 and L2 and theta 2, what do we want to find out? The position of the tip of the robot, which is P of X and Y. What does P and X and Y mean? What is a P of X and Y? What are we saying? P bracket X and Y. Exactly. In other words, the position of P, which is the tip of the robot, is a function of x and y coordinates. That's why we put it in the bracket x and y. If I had put x, y, and z, what would it mean? Three-dimensional, right? In other words, the position of that would depend on x, y, and z. Therefore, it becomes a three-dimensional problem. Where in this case, and throughout your course, we're only going to work in 2 dimensions. So we're not dealing with 3 dimensions at all. So in this case, the position of the tip is of importance to us. All right, so let's make it, I guess, simpler. Again, this represents, the problem that we have. And our objective is to really find out where P is, right? So if I know L1 and theta 1, what do I know? I know the position of, which is this one, right? In other words, I know this. This is like same as the problem we have. And if I know L2 and theta 2, what do I know? Yes?
You can get a big P up there. You can get the, yeah.
So, in other words, look at this diagram. Theta 2 is the angle that the second arm makes with this first link. Okay? So, in order for us to know where P is, I need to know this distance, and I need to know that distance, right? This distance we can easily find from the first bar. I know theta 1, I know L1. What is that distance? X1 equals to? Right, which is L1 cosine of theta 1, which is X1. But when it comes to X2, and if I look at this triangle, okay, this triangle, I know L2, but do I know that angle? Yes and no. It is not entirely based on theta 2, but there's also a portion which is theta 1, because these two lines are parallel, and when a line intersects, these two angles are the same. So in other words, this angle is really a summation of theta 1 and theta 2, which in that case, x2 is simply L2 cos of theta 1 plus theta 2. How many people understand this part? Okay. How many don't understand it then? Yeah, all right. So let's go back to here again. So what I said was x1 is simply L1 cos of theta 1. That part we understand, right? The part that is perhaps a little bit more complicated is x2. In order to find the x2, we should really look at this right angle triangle. And this right angle triangle, in order to use the cosine law, we need to have that angle. But the only angle that we have is only theta 2. What we don't have is that little part here. Let me show you over here. This little part. Let me just go back to pens. All right. So this little part right there, right here. Theta 1 we don't have. So because these two angles, I don't know why the pen doesn't come on. to this. All right. Anyway, it doesn't come on. So the part that we don't understand is theta 1. But using the parallel line theory, when you have two parallel lines, and the line crosses it, these two angles are the same. Right? I'll ask what you have over there. Okay? Two parallel lines, this, and this line crosses them, so this theta 1 and theta 1 are equal. Do you understand? Okay, so now we have these two. So what we need to know is what is x and what is y. As I said, x is simply x1 plus x2, and y is simply y1 plus y2. But what is x1? x1 is? That's right. x1 is L1 cos theta 1. And what about x2? Look at this triangle. This angle is theta 1 plus theta 2. There you are. Okay? What about y? What is y1 equal to? There you are. L1 sine theta 1. And what about y2? Okay? So now that I have x1 and y1 and x2 and y2, I can now find the x and y coordinates. No question? What do I call what? Which one? This one here?
Yeah, that equals theta 1. So what would you call that angle theta 2?
What do I call theta 2? Oh, I mean, so, well, you can call it complementary angle, but in this case, it's really just, yeah, it's a complementary angle, really. But if it was making 90 degrees, then it would have made something different. But it doesn't make 90 degrees, just a complement. So in this case, x, simply because L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to that. So I'm using the concept of trig to find the location of a two-link robot. Again, as I said, your objective really is to find out the position. Yes?
So just to extrapolate further, this is a three-link robot.
Right.
Linking off L2 with the last term being plus L3 times.
Well, it all depends on, yeah, what that angle is, exactly. Because you have to think about it that this rotation of these arms are done by a motor. And the motors basically revolve, right? They don't move things there. They rotate, and therefore the angle goes up and down. So what you have control on that motor is the theta. That's why we have L1 and theta 1. So therefore you know where the location of the end of your robot is going to be, right? When we are looking at robots, with motors, we say is how many rev per minute, so per rev per second. So if you have the rev, how many revolutions, you say only 0.1 second, it would go this far up, therefore it would give you the location of the tip of that robot. All right, so let's go give an example. Now let's say that we want to find the position of a tip of a robot for the following configurations. This one. Theta 1 is equal to theta 2, both of them are equal to 0. So, do we really need to have that formula in order to find out where the tip is? So we can simply observe. If I observe it by observation, what is the x of the tip of this robot in this location? What's that? L1 plus L2. And what is the y? There you are. So, but let's see if we can use that formula, right? L1 cos of 0 plus L2 cos of 0 plus 0. What is cos of 0? 1. So we have L1 plus L2. Exactly the same answer that we had. Okay, so we are verifying both by observation and by following the formula that we just derived. Let's look at another example. This one. Theta 1 is 180 degrees and theta 2 is 0 degrees. Do you agree with this? Well, first of all, theta 1. What is theta 1? Theta 1 is the angle the first link makes with the positive x-axis. In other words, this is theta 1. If I'm going in a counterclockwise direction, is that positive or negative? Counterclockwise is positive. Clockwise is negative, right? So this is theta 1. But why is theta 2 is equal to 0? Right, because theta 2 is the angle the second link makes with the first link. Therefore, it's 0. So that is why theta 2 is equal to 0. And theta 1 is 180 degrees. Yes?
So it's another 180 degrees like 0.
That's right. So in other words, L2 would have been ended up here. Right? It's a relative angle, one with the other one. So, do we need the formula to know where the tip is? So what is the x and y of the tip? X is equal to what? Negative what? Negative? Right, negative L1 plus L2. What about y? And if I use it in the formula? All right? What is cos of 180 degrees? Minus 1. And the second one is cos of, again, 180 degrees. So it's basically minus L1 plus L2. What about the y? The y is 0. And it is because sine of 180 degrees is simply 0. Very simple, right? Let's do one more example. Okay, now, theta 1 is 45 degrees and theta 2 is minus 45 degrees. Why is theta 2 minus 45 degrees? Yes?
The elbow down.
I know, but elbow down because then you're measuring it. Exactly. And it is because it is in the clockwise direction when you are measuring it. The movement is in the clockwise direction. So theta 1 and theta 2 are now known. So, can you tell me by observation where P is? Yes. Yeah, but what is it? What is the value? I know you can show me. What is the value? By observation. That's the formula. I'm just saying by observation. Before we could just observe it, so now you can't. Right? Now you got to go back to that formula. So we have x is equal to L1 cos of 45 degrees plus L2 cos of 45 minus 45. Okay? Cos of 45 is 1 over square root 2 or root 2 over 2. And cos of 0 is 1. So that's what you get. X equal to L1 over square root of 2 plus L2. And the same thing we can do for the Y. So now we are beginning to appreciate that without trigonometry, we will not be able to find the location of a relatively simple problem like this. Any questions so far? Any questions? Yes.
When you go clockwise,
Clockwise is negative, right? Yes. But this has got to be an analog clock. As I said, if you are digital, then it goes like this. So there is no direction. Okay. So now we have an inverse problem. The inverse problem in the robot is now we have L1 and L2 and the location, but now we want to have theta 1 and theta 2. So what does this mean? That means you have a two-link robot. You know where the tip of that robot needs to go, right? So you need to give instructions to your motor by turning in a certain radian or angle so that you can get there. Okay? So this is the inverse. Before we had L1 and theta 1 and L2 and theta 2, and we wanted to go where it ends. But in reality, in day-to-day operations of robot, you know where you want to go, but what you don't know is how your motors must act. And that's what we are trying to find out, theta 1 and theta 2. Do you understand? So the inverse problem actually is more of an application than what you had before. In this case, let's say that we have a location which is 12 and 6, and the links, your robot links, are 5 over, times the square root of 2. Okay? So if I want to plot it, it would plot something like this. So I don't know what theta 1 is. I don't know what theta 2 is, but I know how far, how long my links are, and I know where I am going to end. Okay? So how do I do that? Yes?
You have to find the big angle that would make the 180 with theta 2 first, and then work backwards.
This one? Right. So if you find this angle, then what would that give you? Would this, so you're saying that I have to find this first in order to find theta 2, right? Okay, yes. Well, let's show it in a better diagram, like this. Yes. Go on, go on. It's all right. Nothing is stupid.
No, that's fine.
Yeah.
I was going to say that before you put it out. I'm going to draw a line from the origin to 12.6.
Right. Because so the location of, nothing is stupid except me. So the tip of your robot is at 12 and 6. So that automatically tells you that this right angle triangle, one side is 12 and the other side is 6, right? So if I have this 12 and 6, what do I have? I have this, right? In that right triangle. Based on what theory? Say it loudly. Pythagorean. Yeah, exactly. So that's why you have it as a square root of 12 squared plus 6 squared is equal to a square root of 180. We're assuming that our units here are meters. Let's just stick to meters right now. So 12 and 6 because it's square root of 180. So from this, we easily find that angle. And you're right. So therefore, in this triangle, we have this angle, which is 180 minus theta 2. So if I can find this angle, I should be able to find theta 2. So what do I have in this triangle so far? Huh? Right, I have that side. Do I have this? And do I have this? So just by observing that this triangle, I mean, just, is very specific. This is 5 square root of 2, and this is 5 square root of 2. What kind of triangle is this? Exactly. So which means that these two angles are also the same, right? Okay. So when you have a triangle with 3 sides known, can you find that angle? Based on what? See, he's had this class before. That's why he knows all the answers. All right, the laws of cosines. Who? What did you say? Oh, kudos. Okay. So a squared is going to be. How many people have seen this equation? Yeah. When did you see this? Wednesday. I thought these guys are. So no wonder you know the answer. Did he also give the solution to this?
Yeah.
He did. So should I just stop short and move on?
No.
Okay. So a squared is equal to b squared plus c squared minus 0. I got to check with them so it won't really pass me. So in this case, all we have to do is just put the numbers in there, right? B is 5 square root of 2 squared. C, 5 square root of 2, isosceles triangle, of course. And then 2bc times cos of 180 minus theta 2. So from here, we find that cos of 180 minus theta 2 is minus 0.8. So, what does it mean, 180 minus theta 2? So 180 minus theta 2 is that if this is theta 2, 180 minus theta 2 is this. As I said, if this is theta 2, if you want to measure 180 minus theta 2, the first thing you got to do is you got to get a mirror image of this on the other side. So you have theta 2, which in this case, because it's measured in a clockwise direction, becomes minus theta 2. Therefore, this angle becomes 180 minus theta 2. 180 means from here to here first, 180. You come back by theta 2, and that would give you the 180 minus theta 2. Okay? Why? Can somebody explain why? Come on. Yes.
Because every line has to equal 180 degrees.
Well, first of all, what is 180? You don't know what is 180? 180 is smaller than 200. All right, so 180. 180 is this. Right? So when I say 180 minus theta 2, that means I want to come back, I want to go 180, but then I want to subtract theta 2 from it. Right?
And why can't we do it the other way?
Because your theta 2 is here. So in order to make me visually, make me understand, what I said was, we basically do the mirror image of this on the other side. So this becomes minus theta 2 because it's measured in a clockwise direction. So in effect, what we are saying is 180 minus theta 2. And that is...
You don't have to put the chart on.
No. This is just for... Exactly. This is for visual understanding. Okay? So cos of 180 minus theta 2 is equal to minus cos of theta 2. Why? Because again, as I just said, you are mirror imaging it. So if the cos of theta 2 was this, the cos of 180 minus theta 2 is this. So they are identical, but in the opposite sign. One is in the positive direction, the other one is in the negative direction. Okay? So, in this case, minus cos of theta 2 is minus point S, or cos of theta 2 is equal to 0.8. All right? The signs disappear from both sides. What this simply gives me that theta 2 is an R cosine of, or inverse cosine of 0.8. I hope by now you all have a calculator, a scientific calculator, that you can easily measure what the cosine of 0.8 is. Because you do need it. Then we are noticing that if you look at the inverse cosine of 0.8, two possible solutions come up. One is 36.87 degrees and the other one is minus 36.87. So why is that? Because if you think that if this is your theta 2, right? If this is your theta 2, and this is the side for you finding your cosine, you can find another angle which basically gives you the same thing. Right? They both share the x-axis, but one is in the first quadrant, the other one is in the fourth quadrant. Yes? You don't see it? I'm showing it to you.
No, I can see it, but I don't understand.
Well, because I'm saying that you get two answers. One theta 2 is negative, one theta 2 is positive. But they give you both the same answer for cosine. Well, that's the next thing we want to see. Why there are two answers? Why? So let's go back to your original problem. The original problem was that you know where your robot wants to be, you know the length of your links, and therefore you want to see what angles you should give. This in order to get you to that position. So there are two answers right there. So what is the meaning of two solutions for theta 2? And this is what I'm showing you. There are two solutions. We still do not know what theta 1 is. All right? So if your theta 1 is this, then we call this elbow up. Okay? We don't know what theta 1 is yet. That is why you get two answers. Because if your theta 1 is this one, then you need to go elbow down. Both of these two will get you to the point. The only difference is, in the first one, the motor has to move in the positive direction, and in the second one, the motor needs to move in the negative direction. So if I have two answers for theta 2, how many answers would you expect to have for theta 1? 2, right. So each of them are complementary with one another. Your objective is really to get to this point. And either one of them is going to get you there. Do you understand? Yes.
So basically, not building a robot, you could use it, okay, to position the in two different ways to reach one point.
Absolutely. So And then people question, well, if you have two options, which one should I choose? Okay? So, in those cases, then you want to find the quickest solution. For your arm to move from horizontal to here or to there, which one takes longer? This one? Takes longer, right? So if efficiency is important for me in robotics, and I want to get to that positions fast, then I would go with this one. That's how you make your selection in terms of the positioning of your robots. You may have many solutions, but you want to find the solution that would be the least expensive, the fastest, and the most efficient. Therefore, that's why you go with the theta 1 and theta 2 on the lower end. But that doesn't mean that's the only solution, because there are several solutions that exist. Do you follow? All right, so let's go back to this again. So when we are looking at this, so I want to find out now what is theta 1. So far we found theta 2, right? But now we want to find out theta 1. Now, looking at this triangle, and if you assume that this angle, this little angle, is alpha, right? This little triangle right here, this angle. You see this? If this is alpha, and if I am looking at that triangle right here, tan of alpha plus theta 1 is equal to 6 over 12. Do you follow?
No, repeat that. I didn't.
All right. So look at this angle, this little one here. Okay? Let's call this theta, let's call this alpha. Okay? So what is this angle? This is theta 1, this is alpha, therefore that angle is? Right. So when I'm looking at this triangle, okay, tan of alpha plus theta 1 is equal to 6 divided by 12. 6 divided by 12. Yes?
Why do we have a question like there, but in the book
I don't know. I didn't write the book.
but it's the same. It's the same problem.
All right. So the problem says, in your book, says alpha minus theta 1. So what is alpha over there? Which angle is alpha?
The one, the top, one elbow down, the angle right there.
This one?
Yeah, go up. Yeah, not right there. Right there.
All right. But I'm doing elbow up. Are you looking at elbow up or elbow down?
Elbow down.
But I'm working on elbow up.
They were using tan because what? Tan-
All right. What's that?
They were using tangent because
Because I want to find the angle. I mean, tangent is always giving you the right answer. I mean, if you use sine and cosine, then it might throw you in the wrong quadrants. Okay? So now I have alpha plus theta 1 as 26.57. Right? So, do I still have theta 1? Isn't it congruent of theta 2? Congruent of theta 2. Well, basically, theta 2 is equal to this angle plus that angle. So in other words, in a way, theta 2 is equal to 2 alpha. Right? But you don't know that yet. So let's look at this triangle. So here, you have 36.87. Because this is just happens that this triangle is isosceles triangle. It just happens that way. Isosceles triangle. Because this and this is equal. 5 is square root of 2. But the angle here is alpha. So what we want to find out is what is alpha, right? So in other words, 2 alpha is equal to 36.87.
Isn't also like half of like that are 36.87?
Yeah, because I said this is equal to this angle plus that angle. But that angle is also alpha because it's an isosceles triangle.
So, but you were looking for alpha, right?
I'm looking for alpha, right?
Like, you just like do 36.87. Could you like divide it by 2?
Absolutely you can.
Wait, 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 wait.
No? Okay. There you are.
Oh, there.
All right, so what is your drawing? Okay. Do you all follow?
Yes.
No, he looks puzzled.
I'm gonna look for a while.
Yes.
So alpha is gonna be the same as 36.87 divided by 2?
Yes. Why?
There we go.
Why?
Because it's congruent. It's
Look at this. Well, look at this triangle here. Look at this triangle. Okay? These 3 angles. First of all, what is this angle equal to?
180.
No, what this is this angle?
Oh,
It's the same as this, right? So if you sum these 3 angles, what do you get? 180. So if you get these 2 together, you have 180. Therefore, alpha plus alpha is equal to 36.87 or 18 something, right? Yes. Now, if I want to use, another way is to use the sine, the law of sine. What is the law of sine? The side relative, so it's the sine of this angle over the side opposite to it is equal to sine of this angle over the side in front of it. Right? That's the laws of sine. In this case, it will give us sine of alpha as 0.3164. Can somebody tell me what is alpha equal to?
Alpha is equal to.
Okay, use your calculator.
Oh, okay.
Sine of one angle is 0.364. So do a sine. Yes. Right. Which is equal to half of 36.
So that's sine.
So,
Yeah, go on.
do we have to like use the laws to like find?
No,
We
no,
don't have to.
no. But as I said, this is a very special case because it just happens to be an isosceles triangle. But it could have been something different,
Oh yeah.
right? In that case, you had to use the sine, the laws of sines.
So do you use that for like rectangles?
Do you use it for rectangles? Why
No.
right angle triangles?
Yeah.
Yeah, you can use it for anything you want. I mean, the laws are there, depending on what angles you have.
wait.
Yes.
So we didn't find theta 1 yet.
No. I only find alpha.
I'm confused. That's
So, if I want to find theta 1, what do I do? Didn't you find the value of alpha plus theta 1?
Yeah.
What was that equal to?
Alpha, so 18 minus 26 minus 18. I mean 26 minus 18.
There you are. So now you have found theta 1. So this is one solution which is based on elbow up. Right? Elbow up. Now I want to do the other one. Elbow down. Right? So in that case, the angles will change. So in this case, basically theta 1 is 8.12 degrees and theta 2 is 36.9. The other option was this, elbow down solution, where your first arm goes here and your second one goes there. Now you notice that in this case, theta 1 is the angle that the first arm makes with the x-axis, because that's where your motor is. And then theta 2 is the angle that it makes relative to the first arm. So now that is why you have theta 1 minus alpha in order to get that angle, which is different than the other one, which was theta 1 plus alpha. Do you remember? Yeah? So in this case, again, looking at that triangle here, this triangle, we have this distance is equal to what? And that is equal to 12. So tan of that angle is equal to 6 over 12. But what is that angle? That angle is theta 1, which is the angle that the first arm makes with the x-axis, minus the angle of that triangle, which is alpha, is equal to 6 over 12. So in this case, if you are using the elbow down, instead of theta 1 plus alpha, you get theta 1 minus alpha. All right? So you already found that alpha was 18.45, right? Because the triangle hasn't changed. The triangle hasn't changed. That angle is the same. You've used the isosceles. Alpha is already known, or you use the laws of sine. The alpha is the same. But in this case, theta 1 is 26.57 plus the 18.45. Do you follow? Because you put alpha in here, you have theta 1 minus 18.45. You take 18.45 to the other side, it becomes positive. Therefore, your angle is going to be more than before, or theta 1 is equal to 45 degrees and theta 2 is 36.9.
I was just looking at observation because theta 1 is the whole
Theta 1 is this angle, from here all the way to this.
Right.
Yes. All right? Piece of cake.
This was easier than doing elbow up. Because you already knew everything.
Not really, because in elbow up, you already found alpha. Because you still have to go through the same process within this triangle to find alpha. Because when you were doing elbow up, you found alpha. So if you selected this, so there are two solutions now. Two solutions that get you the same position as far as the robot is concerned. Okay, so that's really simplifying the... Can somebody get a piece of paper and run an attendance? So that basically concludes this chapter. So we're going to move to the other chapter. which is called vectors. All right. How many of you have heard of vectors? Yes. Tell me, what is a vector?
Direction, magnitude.
And a magnitude, right. So now we're, if somebody tells you, where are you heading? I'm heading home, right? So you're giving direction. And then you're saying, well, how fast are you going? So you're also giving it the magnitude. So vectors are actually very important for us because they play really major roles in many quantities. What quantities are measured in vectors? Displacement. That's number one. Where are you? I am 10 yards north of you. That becomes a location, a displacement. How far are you taking it? These are the questions. So the other one is velocity. Example of velocity. I am going 50 miles per hour north, west, northwest, east. Acceleration. How fast are you going? So we're not only talking about scalar quantities. We're talking about quantities that not only they have magnitudes, but they also have directions. Then we can, expand it to force. Electromagnetic fields. Other, examples. So now we are beginning to find out other ways that we can describe the same kind of problems that we've had. So far we have learned about, some algebra. We have learned about trigonometry. Now we're talking about vector analysis. And vector really plays a major role in engineering. So to sum it up, vector has both direction and magnitude. Example, a car traveling north at 65 miles per hour. That's an example of a vector. So how do we show it? This can be represented by a vector on the y-axis with a magnitude of 65 miles per hour. So how do we use this kind of explanation in order to assist us? Now, every step that we're learning from now on is trying to tell you that there's a reason why we are using these type of analysis. And the whole objective is to make it simpler. Simpler so for what you've been doing so far. So let's look at the two-dimensional vectors. So the easiest one is to look at the tip of a one-link robot. Can be represented by a point P. So same robot that we have, moving, theta, and then we want to represent it in a vector format. We said that the P, or the vector P that represents the tip of that robot, must have a magnitude and must have a direction. So we cannot so far now say X and Y. We want to see how can we describe a position vector. So we describe it this way. Wherever you see that arrow sign, it represents a vector, which means that it has a direction, okay, a P bar. And then Px times I bar and Py times J bar. I and J are unit direction vectors. Unit direction vectors in the X and Y direction. So this is how we describe them. I is a unit vector in the X direction. J is a unit vector in the Y direction. What is a unit vector when I say it's a unit vector? Yes?
It has a direction with a specific unit to represent.
Unit means 1, right? It has a magnitude of 1, but it is in the x direction. So rather than me saying that it is 55 in the x direction, I say it's 55i. In other words, I'm giving you the magnitude of my vector, but I'm multiplying by the unit vector in the x direction. So that is how I am describing the point P, which is the tip of my robot, in the x and y direction. Now, before, what we were saying was, in order for me to find the position of P, I needed to know x and y, right? Same thing over here, except that now we are saying that this, in fact, is a vector because it has a direction. It is going in that direction. X in the I direction and Y in the J direction, in the J direction. This is also called Cartesian coordinate system. Cartesian coordinate system, or we call them rectangular coordinate system. Okay, so basics of describing the vector in the x, and what is the magnitude of that vector? The magnitude is the same as before. Is the square root of px squared, which is here, and then py squared in that right angle triangle. Okay, so now I am describing the position of my vector in a Cartesian coordinate system. Yes.
So the magnitude is the same as the distance from it?
The magnitude, before you had L, right? Now we're saying is that in order to describe it in a vector format, your vector must have a magnitude and a direction. So if I am describing my vector as P bar as Pxi plus P by j, so the next thing is, okay, what is P? What is the magnitude of your vector? Magnitude of vector, looking at this right angle triangle, is this distance squared and this distance squared square root, right? Based on that right angle. So now we found the magnitude. So now you want to find out the direction. What is the direction of this vector? Which is described as what? Your direction is theta, right?
Yeah.
So theta is simply a tan 2 or a tan. The reason that I say a tan 2, because a tan 2 also take into consideration the quadrants that your vector is going to be. A tan of py over px. Py over px, which is basically now the direction of your vector. So now I have described your vector in a Cartesian coordinate system. So if somebody gives you a vector like this and tells you, does that vector has a magnitude, what do you say? Yes, and the magnitude is this. Does your vector has a direction? Yes, and that is theta. And it is all based on how you are describing it. Before, we didn't have an avenue to describe it in one line what your vector is. We had to explain ourselves that the tip of my robot was at the x and y position, and the length of that was this, find out what theta is. Now I am simply describing my vector in the x and y direction, or I and j direction, which already has in it the magnitude and the direction. Okay? Any questions so far? So now I want to see, how do we use this? How do we use this in an example? So we say now, given that px is equal to a square root of 3 over 4, and py is equal to a quarter, find the magnitude and direction. So if I have px and py, what do I have? Okay? This is what I have. So I want to describe it in Cartesian coordinate system, the first thing is I want to see what the magnitude is. Or simply P is equal to half a meter. Then I want to know what is the direction. What is the direction? Theta. Right? Theta is your direction. Theta is equal to what? A tan 2 of a quarter over root 3 over 4. Okay? Which is root 3 over 3, or simply 30 degrees. So we can show it this way. This is called a polar coordinate system. The other one that I was showing you was called Cartesian coordinate system. So if I want to show in a polar coordinate system, I give the magnitude, which is half a meter, and I give the angle.
What's this called?
Polar, like poles. Yeah, polar coordinate system. If you want to describe this vector in a Cartesian coordinate system, how do you write it? It would be P bar is equal to
P greater than,
Px, which is the square root of 3 over 4, I plus quarter J. This is called Cartesian coordinate system. That is called polar coordinate system. In a Cartesian coordinate system, you give the magnitudes in the x and y or I and j direction. In a polar coordinate system, you give it that way. If I had written it in a Cartesian coordinate system, what would the magnitude be? Square root of squares of the summation of these two, which is exactly what we got over there. Okay? So now we have two ways of describing a vector. One is called, the other one? Polar coordinate system. Right. So this is called polar form.
So do we use the at sign and do we use that little angle?
Which one?
Because you have an at sign right there, and then you have.
Well, what I'm showing is an angle, but the angle is actually this way. This is the angle sign. You should use it as an angle sign. Now, you know, you got to get used to writing it in radians. We allow 30 degrees because, you know, but if you wanted to write it in radian, what would that 30 be? Pi over 6, exactly. All right, so here's an example in the statics. Those of you, I guess everybody takes the statics in our college. So this is an example. Now you have a person that pushes a vacuum cleaner, right? A vacuum cleaner, going this way, and we want to determine the horizontal and vertical component of the force. Okay? So you have a force of 20 pounds, which is given in a 40 degree angle, or minus 40 because it is in the clockwise direction, right? Or 40 degrees, and we want to find out fx and fy. So what do we do? Yes?
I think for X,
You want to find fx. What do you do for fx? Cosine, right? So how do you do it? Fx is equal to f times
Oh, F times, no?
f times f times f times cosine of, what is that angle? See? It's a cosine. Cosine f times cosine of 40 degrees.
Oh, that was just,
Yes. Okay. F times cosine of 40 degrees. So now you have the fx components. What about fy? Right.
so it's F times cosine of 4. Wait, why would it be a negative 4?
Why is it negative? It's down. Right? So if I want to describe our vector is which one? Which one is our vector? F. F is the force that you're exerting on your vacuum cleaner, right? You guys better get used to it. You're going to be doing that a lot at home. You know, if you think somebody else is going to do it, forget about it. So 40 degrees going down. So you want to describe this in the Cartesian coordinate system. How would you describe F now?
15.32 I with the thing,
A little hat, yeah.
little hat, and then plus negative, no, not plus, minus 12.86 J with that hoodie.
You agree? Okay, yeah. All right, this is good terminology. Hoodie, hat, little thing. All right, so why don't we have it as plus?
Because we have a negative there,
Right?
negative 12. So plus, negative,
Because this is in the downward direction. If you think about up is positive, down is negative in the y direction. Going this way in x is positive, going that way is negative. Okay? All right, so make sure that you note this. All right, let's do another little example. This time I'm going to go into electricity. Impedance of inductor and resistors in series. What is an impedance? What does it mean, impede? Yeah, stop, resist. Very much like resistance. So we have a system now that you have a inductor and a resistor. So when you have an inductor and a resistor, what you really want to find out is what is the capacitance of this circuit. In a capacitance in this case is based on resistance is in the x direction and inductance in the y direction. And when you get to know about electricity, you will see that there is a phase difference between a resistor and an inductance of 90 degrees. That's why when now I want to find out Z, which is an equivalent resistance, or in this case we call it an impedance, Z simply is a vector representing the resistance and the inductance. Okay, so in this case, same as before. R is equal to 100 ohm. X is equal to 30 ohm. Now I want to describe it in the in either a Cartesian or polar coordinate systems. So what do I do? Okay? So what do I do in this case? What is it so different than what I was doing before?
we don't know what the direction is like.
Do we know the magnitude?
You have to use the calculator.
Do we know the magnitude?
No. It's on one.
We want to find out Z, right?
Yeah.
What is the magnitude of Z? based on the information you have? Huh? What is the magnitude of this vector? Yes? R over, I'm saying magnitude. I'm not saying the direction. Magnitude. Magnitude.
It would be the square root of R squared plus XL squared.
That's right. Yeah. There you are. This is called the total impedance. And the phase angle of phi is simply A tan 2. So you want to find the angle or the phase angle, and you want to find out the total impedance. This is yes.
Does this only work for two? Two in the circuit?
No. But if you have 3, then you are either in 2-dimension or you could be in 3-dimension. You remember, when you are, if you put, say, 2 resistors and 1 inductor, right? So you can sum up the resistors together. You still have, because what really matters in this case is what lies on the x direction and what lies on the y direction. But there are other electrical, a capacitor, for example, that might have a 180-degree phase difference, and it would not be in there anymore. It would be somewhere else. But in this case, what you do is you want to sum up the ones that are all fall on the x direction, sum up the ones who are all in the y direction, and you will still have the same problem that we have. Because what we are trying to do is that if you have an electrical circuit, you want to replace this with one simple unit representing all of them. Because if I then have a current between them, and if I want to find that the voltage, all I have to do is just multiply that, the impedance and the current in order to find the voltage. All I'm doing is I'm finding a representative impedance. If you only have one resistor, or if you have a group of resistors here, your impedance field would simply be summation of all of these resistors. But now we have a mixture. You are working in the x and y direction because of the phase difference. So looking at this, I have the vector notation or Cartesian coordinate system. We are showing it Ri bar plus XL J bar ohm, and that's the units of measurement. And if I want to show it in that, this is how we would describe it. So before I found the magnitude, I found the phase angle. Now I'm describing it in the Cartesian coordinate system.
When you do your notation, you have to add the
Go.
the unit that is measured in.
Yeah, absolutely, yeah. They all have to be in the same unit.
No, I'm not saying. I'm saying when you write out the notations, like you have ohms right there, like you have to write out the unit of measurement.
Yes, absolutely. In everything you do in engineering, you have to put the unit of measurement. So because this is impedance, impedance is measured in ohm, very much like a resistance. Right? So in this case, the total impedance is the magnitude that we found from a Cartesian coordinate system. Now, which is the same. The only difference is that we have used different. So this is written in what system? And this? Polar. Two ways of describing your vector. One takes into consideration the magnitude and the phase angle. The other one describes the location. So, if this was a robotic arm, right, and you wanted to describe it, in the motor would only give you the angular displacement and the length of the bar, right? So the polar would be easier to describe than this. Is that the only way we can describe vectors? No. We have other ways too. But why we then describing into two different formats? Because when the time comes and we start working on vector manipulations, then you'll see which one works to your advantage. So one thing is vector additions in your two-link robots. Now you have the position of the tip of the two-link robot. Now we want to describe it in the vector form. How do we do that? And then we want to find out the p and theta. So now you have the same problem that you had, P1 and P2. Now you want to use the vector analysis and see if this makes life easier for us. Same problem. Does it make life easier for us? So when we are summing vectors, we are saying that P, which is your ultimate location of the end of your robot, is really a summation of two vectors. One is P1, the other one is P2. So when we are writing in this format, P bar is P1 bar plus P2 bar, which itself is really Px, which is this, and Py, which is this, times I and j. What is I and j? Yes?
It is the up one. I is the motion and the magnitude in x, and or the vector line.
What did we call it? I and j. I and j. What did we call it? Expand. Come on, don't look at that. Look at me.
You the vector in the x direction.
I and j were called, yes, direction unit vectors, right? Unit vectors in the x and y direction. Unit vectors in the x and y direction. Okay? So now we are describing our, our vector in the x and y direction, or simply in the I and j. So if I'm looking at this, Pxi and Pyj, what in Pxi, which one is a vector, which one is a scalar?
What?
Scalar. What is a vector? Vector has
Direction and magnitude. So it's
direction and magnitude. Right, exactly. So what is the direction of magnitude? What is the magnitude of I? What is the magnitude of I? What do we call it? Unit vectors, didn't we? So what is the magnitude of I? 1. Unit, 1. Unit vector. So I has a magnitude of 1 and a direction in the x direction. J, magnitude of 1, but in the y direction. Therefore, Px does not have a direction. Px simply is a scalar quantity, a value. But when you multiply it by I, means that this whole thing is in the x direction. And this whole thing in the y direction. Do you understand? So when I say P is equal to Pxi plus Pyj, that means this vector has two sides to it. One is in the x direction or I direction, and the other one is the y direction. And the values are Px and Py. So this is how we describe it in a Cartesian coordinate system. And the summation. But then, so then the question is, what is P1 and P2? Right? We have two vectors, P1 and P2. Looking at this diagram, P1 is this vector, right? This vector. So this vector has a Px1 and the Py1, right? Therefore, describing it in the Cartesian coordinate system, px1i plus py1j. Same thing with p2. We have an x2 and a y2, right? So in this px1i plus p1j, which one is a vector and which one is a scalar? Got it. Okay? So all we have to do now, replace it for the value of P1 and P2, right? P1 and P2, we put it in that.
You gotta add all together, get the total.
There you are. Suddenly she's taking this smart position, huh? What happened to you? It's only 3:30. We still have half an hour to go. So,
Yeah, 20 minutes ago.
all right. So P is P xi. So do you understand this part? Right? Summation of two vectors. So what next should we do right here? Can I simplify it? I can. Look at this. I here, I there. Can I factorize it? I should be able to factorize it, right?
I mean, what's the point?
What's the point?
Yeah, we'll just fill it in and just go from there.
No.
How would you factorize it?
How do we factorize it?
Yeah, but you just add separate lines at the back.
Yeah. So now you see, the whole idea is to simplify the process, because if you put it all over the place, you're going to make mistakes. Now, what we are saying is, if you have the two vectors of px1, py1, px2, py2, all you have to do is sum their x components and their y components. Therefore, you will be able to get the resultant, which is your p. Okay? So, do we have px1? Do we have it? So in this case, px of the new vector, which is p, is equal to px1 plus px2, and py is py1 plus vy2. So, conclusion is adding two vectors amounts to adding their x and y components. What's that? If you have three vectors, same thing. So here, in this case, px1 is based on this triangle, right? This triangle is equal to P1 times cosine of 45 degrees, which was that angle. You remember? Are we using elbow down or elbow up over there? Elbow up, right. That's why the theta 1 became 45. Okay? So that's your px1. What about py1? Right. Okay, so we found px1 and py1. What about so this is your first vector. Half I plus half j meters. Next one is to find out px2. Px2 is p2 cosine of 30 degrees. Where did we get this? See that angle up there? This little triangle here? See that little triangle? Okay? So we want to find out px2, which is this distance. This distance is the same as that distance, right? And if that is 30, where do we get 30 degree from?
Oh, I know why. It's because it's a 39, yeah, a 30, 60, 90 triangle. Like, you know what I mean?
Where do you get the 30 degree? Yes.
Isn't it from that triangle that you just said that triangle with like, the hypotenuse of like 1.5 meters? Isn't it a 30, 60, 90 triangle?
I don't know. Where did we get the 30 degrees from? Remember, this was theta 2, okay? And then we had a theta, I'm sorry, this was theta 1, and then we had theta 2. Theta 2 was the angle that he made with the arm. And the angle was 15 degrees. So when we subtracted 15 from 45, we got 30 degrees on the elbow down.
So what I said was wrong.
I don't know.
That's how it looks like.
That's right. So we have the angle cosine of 30 degrees, therefore you should be able to find px2. So you find px2. What is py2? What is py2 equal to?
BX1. No?
Well, there are two ways you can find it. First of all, this is py2, right? This is py2. There are two ways you can find it. You're dealing with a right angle triangle that is 30 degree angle. In a right angle triangle that is 30 degree, the side which is opposite to that 30 degrees, half of hypotenuse, right? So I can tell you that py2 should be half of 0.5 or 0.25 meters. Or you can use the sine system, which is give you the same thing. Okay? Two ways. Which one do you have to use? Doesn't matter. If you are good in, finding the angles of triangles, either one will get you the same answer. So in this case, I should be able to describe P2, which is the x portion of 0.433 meters times I bar times 0.25 times j. So now you have P1 and P2. But your intention is to find P, right? P was equal to P1 plus P2. Vector summation. Right? All we have to do is replace it.
You want to simplify it?
Well, yeah, simplifying means factorizing. So basically you are summing up the portions that are, have I, in this case, 0.5 and 0.433, and 0.5 and 0.25. So this is the vector representation of the tip of your elbow down two-link vector. Okay? Two-link vector in what system? Cartesian coordinate system. Right. So I have the vector. So I ask you, do I know the magnitude and direction of this vector? What is the magnitude equal to? Square root of this term plus this term, 1.197 meters, and a tan 2 of 0.75 over 0.933, which gives you 3879. Is this the same as what we found before? You bet you. It's there. So which one is easier? I think this is easier than all the trigonometric analysis that we did before. So I can describe it now in a polar format too. right? Because I found the magnitude and I found the angle. So I can describe this vector both in a Cartesian coordinate system and in a polar coordinate system. Yes?
We don't have the A-tan too on our.
I mean, it's preferable, but if you do not have A-tan 2, what you have to make sure is that the answer you get for your A-tan, you also check it with what quadrants this lies on. In this case, this is positive and this is positive. So which quadrant is this in? First quadrant. That's why it is between 0 and 90 degrees. But if y, for example, there was negative, then that means it is falling into either quadrant 3 or 4, depending on what x is. And if x is positive, that means you are in quadrant number 4. So whatever angle that you get over there, you have to make sure that you do have a complementary of it in the fourth quadrant. Just taking that into consideration, because many of these will give you the wrong answer. Yes.
So then you could just use MATLAB.
Absolutely, yeah. That's why you're learning MATLAB. MATLAB can help you out in all of this. All right, so let's go do another example. Let's say we have a ship that traveled 200 miles at 45 degrees north of east, then 300 miles due east. Find the resulting position. A practical navigation issue. So we're going north of east by 200 at 45 degrees, and then we are going east at 300. So I want to know, where is my ship? Okay? So now I have P1 and P2. So, yes, you have a question? No? Okay. Oh, now it's easy. 10 minutes ago, it wasn't easy.
Yeah.
Right? So that's a good thing. That means you're learning something, right? So P1 plus P2. So what do you have to do? You have to find? I know, but what is the first thing? I mean, you know that it's a summation of two vectors, but you need to find the vectors first, right? So you need to describe the vectors. So how do we describe it? Let's, P1. P1 is 200 cosine of 45 degrees. So in other words, if this is your P1, that angle was 45 degrees, the magnitude was 200, so it's 200 cosine of 45 degrees in the I direction, 200 sine of 45 degrees J in the J direction, or in the Y direction, right? Why are they both positive? Exactly. It is in the first quadrant, right? Both X and Y, or I and J, are positive. What about P2? P2 is going in the east. Does it have any Y component? Let's go back here. Go back here. P2. We want to describe P2 in the I and J. What is the X component or I component of P2? 300. What is the Y? 0, because there is no reflection on the Y direction. So that's why when we go over here, P2 is simply 300 I bar plus 0 J. Does everyone understand? She doesn't. She's puzzled. She's sleepy. Come on. Go on. Why you don't understand? I'll go back a step. There you are. More? More? Go back here. All right. What do we not? What is it that you don't understand? There is no reflection on the y-axis, right? So that's why P1 and P2 can easily be described in a Cartesian. So now we have P1, you have P2. What do you have to do next? Combine them, exactly. combine them, which means that P is 441.4 I and 144 J miles. So, does that mean anything to you? It's giving you the location. So it's really giving you the X and Y components of the tip. But if I tell you what is the magnitude of this, right? How fast is this ship traveling and where? Does it tell me that? It is. How? In order to find the magnitude from here, what do we do? Right? So now you know how fast it's going. But where is this going? Which direction? 45 degrees? Which direction? Let's go back to here. Let's go back to here. I want to find out theta. I want to find out what is that angle. Right? That angle is not 45. This is 45. That angle is not 0 either. It's something else. It's somewhere between 0 and 45. So when I describe it in the vector format, then I need to find theta, which is the J component over I component, A tan 2. Again, because both of them are positive, because the I and J components are both positive, which quadrants are we in?
Oh, the first one.
First quadrants, right. So it has to be between 0 and 90 degrees, right? So now I have the magnitude, I do have the direction. Can I describe my vector in a polar form?
Yes.
How? How do you do it? You want to describe your P in a polar form. What do? P is equal to? Come on, say it loudly. It's okay. We only laugh at you. Go on. Go on. Go on. Try. That's right. That's it. Oh boy, if you thought something else, then it was a good idea not to speak up.
Yeah, that is why I was like, never mind.
Okay.
I'm not sure what this biology.
All right, so basically now we learned vectors. We could describe it in the, one-link robot, two-link robot. Now we can sum it up. Yes?
For this problem, how do we find out the P2, the angle of P2 was 0 degrees?
What, you couldn't find out why the P2 was 0? Why was it 0? Why was P2 0?
It doesn't have a
Reflected, like,
Look.
So we visually just get the sensitivity.
Well, don't forget, we're only talking about the Cartesian coordinate system. P2 is parallel to the x-axis, therefore does not have any y component. So when you are describing it in the vector format, it does not have any y component. Don't forget, the angle we're talking about is not the angle between this and this, which is not certainly 0. That's another thing. We are now in a different world of vectors. In that case, there is no y components. Therefore, when you describe it in the Cartesian coordinate system, it only has the x-axis or the I component and no j component. Yes?
If you have to describe a line that line is like x equals
Which one? Which line?
the same one we were talking about.
This line? Yes. So if you want to describe it, how do you describe it?
Like x equals
Y equal.
y equals
Yeah. Because y is constant. Right, exactly. Yeah. Yes?
For that tan 2 thing, then, if we don't have it on there, how do you just figure out the angle?
So that's what I said. So if you are, when you're in a situation like this, and if you take the tangent of theta 2, right? Theta 2 gives you the same tan, right? The only difference is this would give you negative, this gives you positive. But if I come to this side, if this is theta 2 and that's theta 2, right? The tangent that you get from here is positive, right? Positive over positive is positive, right? Here, you have negative and negative, but the answer is positive. So when you do the theta 2,
I understand all that, but
Go ahead.
how do you get it?
you take into consideration which quadrant it is in. So if you, for example, if you are in the third quadrant and you still get a, say, 45 degrees, then you say,
I'm asking how you get to 45 degrees.
well, no, because if you get a 45 degree, that means, let's say this is 2 and 2, right? So you say tan of, let's say, minus 2 and then minus 2, right? Let's say it's here. Minus 2 and minus 2, right? So I say tan minus 1 of this, which is tan minus 1 of 1, and that gives me 45 degrees. Okay? But I should know that that is the wrong answer, because minus 2 and minus 2 means that it is in the third quadrant. Right?
Yeah.
So the theta that I get is 180 degrees plus 45, which is 225 degrees, which is this. So if you had the A tan 2, it would give you 225. But because you don't have it, you have to take into consideration the quadrants that they are in. And with an understanding that if the quadrants of the, are in the third quadrant, then theta must be always greater than 180 degrees. So when you get 45, you add 180 to it. Okay? Unfortunately, that's what you have to do. In the high school, you never bothered with that because you only wanted to get their answer for the Tirek. But when we are talking about the engineering, then you have to take that into consideration. All right, so that means the end. That's it. All right, very good. Not with me. You're going to stay here and you're going to enjoy the recitation. I know you love to spend time with me, but... All right, so far so good?
Yeah.
All right then, thank you.